Thank you, Allison. I didn't actually come out here just to give this seminar, believe it or not. The real reason to be here is that Hanwha has established a collaborative research agreement with Allison and some of her students here at UNSW in concert with also support from Suntech, which I think is kind of I hope a watershed achievement in the sense that we've got two major competitors in the space actually collaborating together in conjunction with a major university, and it's something I would hope to see replicated more in the future. But while I'm here, I had to say something. I can't say anything that's proprietary, so I chose a completely off-the-wall subject, which is about designing experiments. I happen to have received what we call in the US a minor. It's kind of like having a double degree program here. My minor was in statistics, so although I was an electrical engineer primarily, I also got heavily into stat. And then I never did anything with it until I actually got into doing experiments, and I suddenly realized there might be some interesting opportunities to actually apply some of these ideas, and it's actually turned out to be very useful throughout my career to do so. However, I only learned that relatively late in my career, so I'm going to start off by asking the audience here, has anyone ever had the luxury of doing an experiment and replicating exactly the same thing a second time to see if you get the same answer? Oh, congratulations. Okay, a few of you have. Okay, that's very good. I know the first time I did that, I was a bit shocked when I got the different answer the second time. And it really sort of hits home the basic idea that you have to be careful about always believing things when you see them the first time. And it's especially hazardous if the thing you see the first time is what you were hoping to see, because then you will almost certainly not replicate it for fear that it might not work the second time. So in fact, sort of addressing students in particular, I mean, one great result will look really nice in your thesis, but you have to really consider the ramifications. I mean, what if it was really just a lucky coincidence, and even yourself can never repeat that again? More important, maybe as you start thinking more broadly, what if another lab tries to confirm what you've published and they can't get the same result, and they start, slamming you in the press, so to speak, because what your result must be rubbish. And then more importantly, if you're in PV, you have to think, well, will it actually have any impact on high volume manufacturing? Clearly not if you can't even replicate it yourself. So I've established some general rules, call these rules of thumb if you want, for whether something is a real result or just a fluke. And it really takes three, what I'm going to call independent replicates, in order to have a trustworthy estimate of the average of any measurable thing. Say it's a process. Maybe it's the efficiency of a solar cell made using a particular process. If you have less than 3 replicates of something, you should always have a little bit of doubt in your mind as to whether you really are reporting an accurate long-term trend. It's even harder if you want to get an estimate of the standard deviation, or in other words, the variability of that process. It takes really at least 10 independent replicates of something to get a decent estimate of what the standard deviation is. I've occasionally seen people publish, a standard deviation based on 2 measurements, and that's kind of almost a meaningless quantity, really. Now, I've put independent in italics here because that's really a critically key element in this. Data are not independent of each other unless the individual values sufficiently capture the various sources of uncontrollable variation in the process that you're measuring. And in the work that we do, those are most often cell-to-cell variations. I mean, maybe even between 2 cells that are small cells on the same wafer, you're going to see some variation between those. You clearly are going to get wafer-to-wafer variation, and that can be quite large if it's a material like multicrystalline silicon. But there's other things to think about. Day-to-day variation. I mean, what you get today may not be the same result you get tomorrow, even though you thought you did everything the same. And then, of course, there's other things that you can ad infinitum. There's tool-to-tool variations, person-to-person variations, and ultimately lab-to-lab variations. So let's take, for example, if we had 8 small cells on each of 10 wafers, and we process those wafers in 2 different batches of 5. Well, in my experience, if the material you're dealing with is multicrystalline silicon, you capture a lot of the variability. The primary source of variability in those cells is probably the material itself, the nature of the grain boundaries, their density, the intra-grain defects. So quite often, every one of those 80 cells can be considered to be statistically independent of each other, and that gives you a huge amount of statistical power in your experience. Unfortunately, that statistical power is balanced by the fact that the material is highly variable, so you're going to have a large standard deviation, but the statistics works in your favor to help make it a reasonable comparison. If you're dealing with monocrystalline silicon, the material is almost perfectly uniform, frankly, and so unless you have some problem with your process, chances are that all the wafers are essentially the same. The main source of variation actually is going to be the batch-to-batch processing variations, in which case, in the example I've given here, there's really may only be considered 2 legitimate replicates in that situation. And all you can really do is use the average of one batch and compare it to the average of the other batch. You can't really try to represent that you have 80 independent cell efficiencies there. So, sort of starting from the bottom and working up in this talk, I mean, a typical thing that you get faced with when people ask about statistical significance is you're just trying to compare process A versus process B. And people will ask, well, are they statistically different? Well, what does that even mean? Okay, typically, statisticians at least use this threshold barrier of 5%, meaning you want there to be less than a 5% chance that the observed efficiency difference, or whatever the difference is, whether it's voltage, efficiency, you name it, less than a 5% chance that the difference is actually just due to random noise. Now, what does that mean? It's kind of phrased in a backwards way. It's saying to prove that 2 things are different, you want to be able to say there's less than a 5% chance that they were really the same. So we have this thing called a p-value, which is this probability value, which is talked about a lot, and it shows up all the time if you use one of these statistical programs like Minitab or JMP, for example. And if this p-value is less than 0.05, it's telling you that there's less than a 5% chance that they're actually the same, and therefore the better process in your comparison is in fact probably the better process in the long run. If p is greater than 0.5, then it's hard to really interpret what that means. I mean, it could mean that you just need to collect more data to increase the statistical power of the comparison, or it could be that really, in fact, the difference just isn't important. Now, people will often say, well, does that mean that there is no difference? And this is a bit of a paradox in these things, because 2 processes, if there's something different about the process, I can guarantee you that there is a difference in the performance. And if you could do 1,000 replicates of this one and 1,000 of this one, you would see that difference. But if the difference is 0.01 percentage points in efficiency, who cares, right? So you have to actually sometimes start talking not about whether things are different, but whether the difference is important. And that's where I'd say experience and knowledge in the field becomes really important. And it's the sort of reason why it's a little bit dangerous to just turn over issues like this to a statistician who has no background in photovoltaics, because they would be unaware of what is important versus unimportant. So what happens if you make conclusions based on results that are not statistically significant? Well, in my experience, it very frequently leads to a great deal of wasted time and effort. It very commonly occurs when their first result is the one that was desired. And why? Well, because people like to see what they expect, and frankly, people don't like to repeat the same thing more than once. I mean, it's really hard, once you get a result, especially if it's a good result, to go back and do it again and risk the possibility that your hopes will be dashed and you'll find out that it was a fluke the first time and it's actually impossible to replicate it. What I've shown right here is sort of a typical output from, I happen to use Minitab. In the company I'm in now, actually most of the people that work for me use a program called JMP or JMP, but they're the same thing, just 2 different brands. And I just did a typical thing, and I ran through some data. In this case, there's, if you can see the numbers on here, 3 replicates of a new process and an old process, 2 different means and 2 different standard deviations for those groups. And it comes out with this p-value, which is less than 0.05, which tells me that there's a statistically significant difference between these things, assuming, of course, that these are 3 independent replicates. So you have to ask yourself that first. Now, a common thing that's done is to, instead of working through a program like this, because these programs aren't cheap, I think a single user license is like $1,000 or something like that. So what you can do, though, is if you can construct these confidence intervals for each of these 2 processes, which has the means marked here and what's called the confidence limits on those means shown here, and I'll explain that in a moment. If the mean of each process lies outside the confidence interval of the other process, then you can generally say that will be very close to what we mean by 95% statistical significance. Now, what if you don't have one of those fancy programs? So I call this do-it-yourself 95% confidence intervals. So you really just have access to this table. I'll leave a copy of these things behind so you can look this up easily. But this is an in statistics book as well. There's this thing we call degrees of freedom, which I'll explain in a moment. But once you look up how many degrees of freedom you have in the calculation of your standard deviation, you look up this t value, which stands for something called student's t, which you don't need to know what that means, but it's a statistical measure. And you look up what this number is, and you plug it into this little formula down here, along with a calculated standard deviation from the data that you collected, and the means, and the number, which is very important. How many replicates did you have for evaluating that particular process? In this case, in that previous example we had, it turns out that df is 5. And you're going to say, well, how did I come up with that? Okay, so degrees of freedom is the number of data points that you use, that you have available, total, which in this case was 6, because there was 3 and 3. But then you have to start subtracting from that, did I say 5? Actually, that should be 4. Okay, I'll correct this slide. Because there's 6 values of data in this case, but we have, from that 6 values of data, we've calculated 2 different mean values. And if you read this footnote, it says you take the number of data points minus the number that are used to calculate means. So you look up the number, plug it in, go back, figure out the standard deviations for each of the 2 groups of 3, do a root mean square combination of those, that gives you this number. You have the number of each one of these, you have a couple of means. You put that all together, and you can generate those nice pictures showing, this is not, let me be clear, what we're not doing is measuring the mean and the standard deviation of the data. We're measuring the mean and how well we believe the value of the mean for each of the 2 groups of 3. And they're 2 very different things, and it's critical to understand that. If this is a very quick introduction to it, if that flew past you just then, pay some more attention to it, because it's really important, especially when you're looking at error bars in people's publications. Usually when people talk about error bars, they're talking about confidence limits on the mean. They're not talking about the distribution of the results that were obtained for that process. They're 2 different things. All right, now, having done that simple A-B comparison, that's nice, but that's not yet really a design of experiments. Typically, you go into some sort of a study and you have to ask yourself, okay, usually you want to optimize something. Now, what optimum means will be very different depending upon the circumstances. But if you're in this scenario, it's probably you're trying to get the best efficiency you can get. It might be that you're trying to minimize the number of steps in order to obtain an adequate efficiency. There's a lot of different ways to define optimum. But in any case, if you step back and think about it, there's a whole lot of knobs you can turn to try to make this thing better. So we call those knobs the experimental factors. And you have to ask yourself, how do you choose these in the first place? So my recommendation is that you start by trying to make a list. This is kind of a brainstorming step. Think of all the factors that might affect your result. And at this stage, it's much better to be all-inclusive than to overlook something that might turn out to actually have been important. This next one is really important, is to decide which of those factors are actually readily controllable and which are not. Because there may be a lot of things that you admit it's going to affect the result, but I really can't control it. Either it's because you're in a lab environment where the person who used the bath before you may or may not have contaminated it. There's a whole raft of things that you just may not be able to control very well. If you rank then the controllable factors by what you think is going to be their significance, in other words, their effect on the performance, cost, repeatability, whatever it is, then you might say, well, how do I do that? I haven't even done an experiment yet. Well, this is why you learn how to read papers, go to conferences, talk to colleagues. I mean, there's a lot of ways of obtaining input to try to get it to estimate as best as you can which of the factors you actually expect are going to be the most significant ones. And then when you design your experiment, you try to, obviously the experiment will test the factors that you think are important, but now this is where most people slip up. It's actually best if you try to design it so that it uniformly and randomly samples all of the uncontrollable factors. Now this is where there's a huge divergence of philosophical approach, and typically one can almost say the universities tend to go off in one direction and industry tends to go off in another direction. What I'm about to try to sell you on is usually considered to be the industrial approach to this. So, meaning, I guess, that you've probably been taught, going back to high school, that rather than trying to sample a wide range of the uncontrollable factors, you should do everything within your power to make sure there are no uncontrollable variations. Meaning down to the point of doing the whole experiment between midnight and 4 a.m. in one shot, if that's what it takes to make sure that nobody changes anything during the course of your experiment. In industry, we're not so concerned about that because we don't want to have to only do production between midnight and 4 a.m., for example. So we look at things in terms of saying, no, let's do one of the experiments at 1 a.m., let's do the next one at 5 a.m., and let's do another one at 2 p.m. That way, if there's some daily routine thing that's changing things, we will have sampled the entire random space associated with that. Now, how many factors is a reasonable number to take? Well, it turns out if you pick too many, you'll spend your whole life just sorting through these screening factors. So it's important to have done enough what I'll call literature search to have at least reduced it down to maybe 4 to 6 of what you think are the most important ones. Now for each one of those, you've got to choose a range within which you're going to study the effect of that factor. Now, it helps to start by picking a nominal midpoint, and sometimes there's already a current best practice for that process. That would be a good starting point for a midpoint. But then you have to pick a range. So you pick a high value, a low value. It's quite important to try to do this in such a way that you don't inadvertently pick a high value or a low value where the process simply completely fails, because you're not really going to gain yourself much information if you do experiments in a regime where it doesn't work at all. And I'm going to be using alkaline etching as an example here. So a classic case with alkaline etching is there are certain regimes where you don't get pyramids at all. You just get a planar surface when you're done. So that really isn't a very useful part of the parameter space to be investigating. After you've chosen these two limits, it's useful from an experimental point of view, from the statistics at least, to go back and readjust your midpoint. And the reason for that is the statistics works better if the points that you're selecting include a midpoint, two limits, and the midpoint is in the middle in some way. Now you can define middle in at least two ways, and that's either as an arithmetic mean or as a geometric mean. And in fact, there are some people sometimes ignore the geometric mean option, but it's really pretty useful for a lot of things, because a lot of the processes we deal with, you have to like double something in order to get a significant change in the process. So, you might want to look at 1%, 10%, and 100% concentration of something. Well, that's perfectly legitimate. In that case, the 10% is the midpoint of that geometrically scaled, or call it exponentially if you prefer, scaled factor. Now, in order to screen these factors, there's a variety of ways to do it. You can sit there and do what's called one factor at a time. You sort of hold the other factors constant while you scan the one. Well, that's okay if you're on a really limited budget, but it turns out it's not the optimal way to explore the parameter space. You can do a full factorial. That's all possible combinations of the high and low limits of all the different factors. That's really gives you nice results, but it's very time consuming because that's a large number of experiments to run, and most people don't have the time or the resources to do that. So there's something called a fractional factorial, which is a really nice compromise, which is pretty much recognized as being the optimum solution for this. There's different types of fractional factorials, and if you pull up one of these design of experiments software packages, it'll give you options, and I highly recommend the ones that are called resolution 4. You might say, well, what the heck does that mean? Well, a resolution 4 experiment is one that has at least enough points tested within this multi-dimensional space to make sure that any effects that are deduced from the experiment are not contaminated by interactions between other factors. And that's an important thing to do, because sometimes interactions between other factors can be pretty significant, and if you misinterpret that as being an effect due to this third factor, you'll be completely off on the wrong course, and that's not a good thing. So just as an example, an alkaline texturing process, which has sort of been historically in photovoltaics one of the more difficult things to optimize and to maintain in proper form. I mean, some of the controllable and important things are like the concentration of KOH, or sodium hydroxide, the time of the etch, the temperature of the etch. Some things that we know are controllable, but typically are less important is the concentration of any additives that you may put in. I mean, IPA is one such additive, but the industry is largely moving away from that now towards higher boiling point alcohols. But anyway, these are you know, there's a fairly large range of these things you can put in. It doesn't have a huge effect on what comes out. And then there's this number of wafers. I mean, if you have a certain solution, you know, you're going to get different texture if you dip 5 wafers into it than if you dip 10 wafers into it. But it's not a huge effect. It's something that you know, okay, someday we'd like to study this, but maybe not initially. Then there's uncontrollable things. The silicate concentration in the solution is hard to control because even during the etch itself, you know, the silicon is consumed and the silicate concentration goes up with time, even during the one experiment that you're trying to perform. So that's very hard to control. Wafer orientation, if you've got saw marks on it, you get a different type of etching if the saw marks are horizontal than if the saw marks are vertical. But you don't really want to have to control that all the time. It's just a too hard basket. And then the surface roughness, same thing. I mean, wafers that are diamond sawed are going to have a different roughness than wafers that have been slurry sawed. And you really would like to have a process that doesn't care about that when you're doing this. So I would consider that an uncontrollable thing. So I didn't put the numbers on. I just labeled things -1 to +1, with 0 being the midpoint, so as not to get into proprietary details maybe. But here's an actual result for a process involving this alkaline texture. Now this is an interesting one because at this low value of temperature, there's a large regime here, this light green, where this is by the way, this is the reflectance of uncoated silicon after the texture etch. So if it's bare silicon, you expect it to be about 36% in the wavelength range being tested here. If it's perfectly textured, it's in the order of about 13%, which is what we would expect to have for this. So there's a large range of parameter space here where essentially that you get a planar surface when you're done. You haven't gotten any etching effect. There's a little bit of something going on down here, but now this is sort of interesting. So if I start to increase the temperature, these contours, if you want to say, are going to move, and you can start to see a growing area of pretty decent texture occurring as it moves up in temperature up to, here's the midpoint. Now this dark blue is essentially perfect texture being obtained within that regime of the parameter space. And then as we go up in temperature, that optimum starts to shift to shorter times and higher values of KOH. Now that's the reality, but of course I'm omniscient in this case because this is the result of collecting a huge amount of data. When you're starting out on this, you would have no clue that this is what you actually were dealing with. And the question is, okay, how would you start going about trying to explore this sort of a space if that was your intent? Well, you might start out with doing one factor at a time, and probably you would start by taking the middle temperature and the midpoint in time, and you would maybe vary the KOH from a low value to a high value. And if you do that a whole bunch of different KOH values, if you had a noise-free experimental environment, you'd get a nice, like perfectly parabolic curve like this. The world is not noise-free, so this is what you would get if you had had that though. But you might have chosen a different point. You might have chosen the low temperature and long time, and in that case, the KOH, you never get as good for any value of KOH. And you run into this problem at these high values of KOH, you essentially start getting into a planar etch instead of a texture etch, and it sort of saturates up here. And this is the sort of thing that drives statistical experimentalists crazy, because most of the stuff that goes on in this analysis doesn't allow for saturation effects like this. It assumes, normal probability distributions and smoothly varying functions, and there's a lot of underlying assumptions in the statistics that can run into trouble if you get into something like this. So in the examples I'm going to do today, I'm going to include one that sort of flirts with this problem to see how much it influences the result that comes out of the statistical analysis. So to do that, it takes a long time to do experiments. Okay, so it's much easier to do something in Excel. So having already now that enough experiments have been done to know what the actual three-dimensional response surface is, as we call it, for this process, I can plug that in and then sort of artificially add noise at various points in the parameter space. And this just happens to be the Excel formula that you would use for adding noise with clamps. So this one is clamps, so no matter how much noise you add, it can't go below 13% reflectance, and it can't go above 36% reflectance to represent the fact that those are sort of physical limits that are imposed on this particular process. So a typical question that you might start asking is, okay, if I want to examine even just one parameter, where should I sample that parameter? And I'm going to compare it. There are two different things going on here. The top two things here is you uniformly spread your points between the low and the high value. In this case, there's a total of 9 points represented there. The two bottom curves are, I say, oh, forget that, I'm going to do 3 replicates at the low value, 3 replicates at the midpoint, and 3 replicates at the high point. Now, the left column is for a sort of a reasonable amount of noise of 1 percentage point in reflectance. But I can also simulate, because this is an Excel simulation, what would happen if you had like really poor process control on this thing, and the noise inherent in the process was more like 5 percentage points in the reflection. So let me just start with the reasonable noise scenario over here, the 1 percentage point. So you can see what I've done here is I simulated 5 different runs of this experiment. Each experiment was 9 different KOH concentrations. And I said, okay, suppose I did that 5 times and compare what I got those 5 different times. Each time I would plot the 9 points and I would fit some sort of a parabola to it to try to estimate where the optimum KOH concentration is. And if I take the standard deviation of these, actually not just these 5, but then I went and replicated this actually 100 times in order to get a good estimate of the standard deviation. There's a standard deviation of the KOH value at the minimum reflectance point, and that standard deviation is about 0.03. And you might say, well, what are the units here? Well, this is on the scale of -1 to 1. It's pretty good, really. You know, it's only plus or minus 3% on that sort of a scale. But it turns out, interestingly enough, if you take the same amount of effort, which is 9 runs, and concentrate them all at the high, mid, and low points, it's more consistent. It's more consistently points you to the correct optimum point than by spreading the points across this range. And that's pretty interesting, I think. You might say, well, 0.03, 0.02, those are both pretty small numbers. But keep in mind that there's sort of a fundamental basis in statistics that in order to improve your knowledge of the mean by a factor of 2, I'm flashing back to that formula that I had up at the beginning, the m plus or minus blah, blah, blah stuff. There was a square root of n in the denominator. So if you want to narrow your certainty about where the mean is by a factor of 2, you have to do 4 times as many experiments to do that. So a factor of 2 in standard deviation is kind of a big deal. So this is like a factor of 1.5 in standard deviation. It's actually non-negligible, and the fact that you got it without any extra effort sort of strongly points that this is really the better way to do it. Now, how often do you see this in publications? Almost never. I tell you, people like to have all the data points, you know, so they can show that, you know, the trend from start to finish. Question? Yeah. By the way, questions during the are okay.
But in this case, you assume you know already the function.
Okay. Well, I can show you examples where it's not the case, but it turns out you don't have to know the function. You only have to know that you expect an optimum between the high and low values to make a parabola a perfectly reasonable fit.
So a parabola is a function.
Yes. So if you and I've glossed over a point before this where when you're doing the screening, initial screening of the factors, you test all those corners in the parameter space, but it's always important to also test the midpoint. Even if it's a 10-dimensional space, you also test the midpoint. And what you can do is compare the value that you actually observe experimentally at the midpoint compared to interpolating all the corners to the midpoint. And if the value at the midpoint that you observe is significantly higher or lower than the interpolated value, it's a good indication that there's either a peak somewhere in that space or a minimum in that space. In this case, since we're looking for an optimum process, we're looking for a minimum, in this case in reflectance, or it would be an optimum in efficiency. And so the simplest function that detects a minimum is the second order function, a parabola in 1 dimension. So that's the reason for using a parabola. Yes?
A simpler illustration is just if you're fixing a straight line, put your effort at the ends.
Yeah.
So 2 points determine the line.
If
As long as you're
right.
confident that you're given the line.
Right. So if you don't already have data suggesting that there's a minimum or a maximum, and your first order assumption maybe is that I just want to know whether that's better on the right or on the left, then you're definitely better off focusing your effort in testing the two extremes rather than spreading points across the entire range in between. And it may be a little counterintuitive, but it works that way. And it has the side effect, which is very useful, that by replicating exactly the same process multiple times, you get a very high confidence in how much random variation there is in your process. Whereas if you do this multiple times and you get some things going up and down, then you're just kind of left going, well, is that because it's a complicated function, or is it just because there's noise? And this becomes much more evident when I increase the noise to 5 percentage points. And here it's sort of blatant. I mean, I've got at least one of these 5 runs, if I did a parabolic fit to it, it actually shows that it's worse in the middle and it gets lower on the sides. And for the other 4, at least they show that the minimum is somewhere between the two extremes, but it's kind of all over the map. The high, mid, low one, it's noticeably better in this situation where you're dealing with a lot of noise. So, and here you can see that the ratio of the standard deviations, again, is of comparable magnitude here. It's just that the numbers are a lot bigger, and so graphically it looks a lot more impressive. But you can see if you got something like this, you'd be really wondering to yourself, is this like a 7th order polynomial I should be fitting to this? The answer is probably no. Don't waste your time on that. It's probably a simple underlying process with noise added on top. Yes?
So would it be valid to do like a single fit through all of those points on the top right? Correct.
If you had the luxury of having done this many experiments, yes. Clearly you'd be better off to, for example, average the points at each point and fit through that rather than this. But what I was trying to show is if you only had resource to do 9 runs and you had to live with whatever you got from that. Was the point here. So what if you got 2 dimensions? Okay, that was 1 dimension. What if you got 2 dimensions that you want to study? So this is the 2-dimensional analog to uniformly covering the available parameter space. And this is the 2-dimensional analog of sort of just doing the extremes. Now, if you're only looking for linear effects, you only have to test the corners. And then again, it's always a good idea to also test the middle, just as a verification thing. But if you expect that there's a minimum or a maximum within the space, then in order to figure out where that minimum or maximum is, it turns out you also have to test edges as well. But when you're deciding how to allocate where the points are, you have a little bit of freedom. Now, in order to make these two things comparable, it takes 16 points to do here. So I said, well, I'll distribute my 16 points over here by, in fact, putting all 4 of them in the middle. That gives me a good replication and statistical estimation of how much noise there is at that point. I've got 2 in each corner and then just 1 each at these various edges. Now, to make this even more challenging for the statistics, you'll notice that I happen to pick a temperature, which is the midpoint, where in 2 of the corners, the process has failed. There's no texture at either of these 2 corners. And you might say, well, surely that kills trying to use this idea because we've got a significant number of our runs here that we've allocated to these 2 corners where we don't get any texture at all. It does have an impact, as we'll see, but in fact, having tested whether that works or not, I'll give you a glimpse of the future. This will in fact turn out to still be the better way of doing things. And here's how I tried to represent that. And this is challenging perhaps, but I essentially, again, because I can artificially add noise at will using Excel, I can simulate having done this experiment, in this case 100 times, both with the 1 percentage point of noise and with 5 percentage points of noise. And I can say, well, where does the resultant experimental data tell me the optimum KOH value is and the optimum time value? Those were the 2 axes of this 2-dimensional study. And I've compared here for the corner edge center approach, which I'd say is sort of the designed experiment approach, or the uniform spread approach, which is kind of the brute force approach, if you want to use. And the differences are not huge in this case. And again, the corner edge center is hampered a bit by the fact that you've spent a fair bit of your effort on these 2 corners where you don't get any texturing at all. And the values you get there are not very representative of what's going on in the interesting part of the space. But despite that, you can look and see that, by the way, these arrows show where the true optimum is. And then the histograms show how often out of these 100 different experiments you get the experiment points to an optimum, which is in these various intervals. It's actually, if you look at them closely, you'd have to sort of conclude that the corner edge center is actually better than the uniform spread or is more likely to give you an answer close to the true optimum compared to the uniform spread approach. If you get up to a large amount of noise, it gets really messy. And in fact, you can see you can be pretty far wrong sometimes on these things. But for the most part, with the possible, this one's the messiest one, where I'd have to say the two are approximately equivalent. Here you're a little bit better off with the corner edge corner, but not a lot. So if you have a very noisy system, I would sort of end up concluding that, well, you're not any worse off using the designed experiment approach. But if in fact your noise is better, not as bad, then you're slightly better off. And that's despite the fact that two of your corners failed in the process. If you don't have the corner failure, then you clearly get a better result with the designed experiment approach. What if you want to do 3D? Okay, so now I'm back to, okay, I'm sampling a full three-dimensional space. Where the heck, that's a lot of space to cover. But you could do it with what's called a corners, faces, center approach, where we've got 8 corners to that three-dimensional cube. There's 6 face centers in that cube. And let's do 2 replicates of the center point. That would be a total of 16. That's quite a few runs, I admit, especially in a university environment. But it's not a ridiculous number of experiments to try to do and to explore a three-dimensional space. So I simulated doing that, again, by throwing in my 1% of noise to make the statistics have to do their job. And this is in this particular case, this is the answer I got for one such thing. Of course, you would get slightly different numbers because noise is noise. It would be different every time. But they're not hugely different. And in this case, you get this output, and you start looking at these p-values. Now, what do they mean? So this tells you that the effective time, temperature, and KOH concentration, none of them are less than 0.05. So I can't actually say with statistical significance that any of those 3 factors are statistically significant, but you have to be careful what that means. What that means is that comparing the high value versus the low value, I can't be sure whether high is better or low is better. But that doesn't surprise us now that because we know what's actually going on here is that there's an optimum in between. So it's just telling us that the high and the low are about the same. But what is significant is these second order effects. So you see there's this 0.034, 0.022, and this one's really small. So there's a second order effect in time, which is really important. The second order effect in KOH that's important, and there's an interaction between the time and the KOH that's important. So that's essentially telling us that, okay, you may not be able to tell the difference between the high and the low limits on these things, but there's something significant happening in between that's real. There's some other things that appear to not be significant. The squared term on the temperature, interaction between time and temperature in this case, and interaction between KOH and temperature, they didn't rate in this analysis. Now, this is a really hard number to come up with, but fortunately these advanced programs crunch it out for you. But this is the standard deviation of the measurable thing, which in case is the reflectance, after accounting for the effect of the factors. So if you took the standard deviation of all 16 numbers that you got, you'd have a huge standard deviation, but that's because you're changing the parameter values with every run. And so you get some with 36% reflectance, some with 13% reflectance. I mean, it's all over the map. But after you've fit the data to this model, then you can say how far is the data at each point away from the model value. And then you can represent that as a standard deviation of those residual noise values. And it comes out to be an interesting number. It's not the 1% that I originally stuck into the model as the noise. It's higher than that. And the reason is because this represents both modeling error and noise error. In this case, the modeling error is primarily due to the fact that there's this model is second order in the terms, but the reality of the process that we're measuring is not second order in the terms. It's got plateaus and saturation points and various other things going on. And so the modeling error in this case is definitely the larger component. And in fact, I was able to, because I knew that the 1% was here, you can separate these out because this ends up being a root mean square combination of the two values. So in fact, in this case, the modeling error was the dominant thing, and it's mostly due to this process failure or saturation in the extremes. So just out of curiosity, if you take the model that came out of doing this, so remember what we did, we had the original thing that started. We have now added noise to it artificially to replicate, having actually done an experiment to sample this space, stuck it into the program, came out with these parameters and coefficients. This is the model that that it thinks is the reality after I've done that. Of course, now this is going to be a perfect second order shape in this three-dimensional space because the model is a second order model. But I think you'll see as I step through them here that although the details are not exactly the same, the basic trends are actually remarkably similar to what we saw is the reality from which this was derived. If we actually go back and say, okay, we started this whole process with a midpoint, which was the old process that we had, which was 0, 0, 0 in this normalized space that I'm presenting. This new thing that I've just shown up here, if I step backwards on it and say, well, where's the actual optimum? It's somewhere in here somewhere, I think, and it would be, near the midpoint of this blob or something. I actually worked through that in more detail and came up with this point. So it's with a time that's a little more than the midpoint, a temperature that's a little bit higher than the midpoint, and a KOH concentration that's a little lower than the midpoint. So this sort of tells me that the thing I started with wasn't terrible, but after having done this experiment, I would conclude that this is probably a better process. But is it? And that's always an important thing to ask after you do this. So when you think all is said and done, it's really important to go back and validate your conclusion. So what I did here was say, okay, suppose at the end we went back and we ran the old process once, found out what the reflectance was. We run this new process once, find out what the reflectance was. Well, what sort of numbers would we get? Again, I didn't want to do this 1,000 times in the lab, but it's easy to do it 1,000 times in Excel by taking the numbers that I should get and adding this random noise component to it to represent the experimental factor, or excuse me, the experimental variation. And here's what you get. So this is the red bars here represent, of those 1,000 such attempts, it looks like most of them tend to give you a reflectance that's here in the mid-15s or something, but occasionally you'll get numbers as high as 18, or maybe numbers as low as 13. The new process is interesting. It's highly skewed, and it's very much not a normal distribution. The reason for that is because once the surface is essentially perfectly pyramidally covered, the reflectance goes to 13%. You can't do any better than that. It's as good as it's going to get unless you start adding anti-reflection coatings or something. So if I did the 1,000 runs here, this is what I get for the new one. Now, looking at these color bars, it's pretty clear that this new process looks better than the old process. The reflectance is generally lower. But in fact, if you only did each of them once to say, now let's prove that the new process is better than the old process, the new process would in fact only come out better 86% of the time, because there's a number of these red bars that are to the left of some of these blue bars. So occasionally you're going to, shall I say, get unlucky. And when you test the new process, it's not going to be as good as it always is. It's going to be kind of on one of the less good runs of that process. And you might test the old process, and it'll be one of the randomly better runs of that old process. And 86% is not a really comfortable number. So I'd have to say, okay, at least in a situation like this where you run into non-idealities like non-normal distributions and the like, probably a one against one test at the end is not adequate. And I'll flash back now to one of the points I made at the very beginning, that really if you want to have a good estimate of the long-term average of something, you need at least to do it 3 times. So let me take my own advice and do the same thing, but this time I'm going to do 3 runs of the old process, 3 runs of the new process, same background noise, but now I'm going to only look at the average of those 3 old process runs and the average of the 3 new process runs and see what I get. Turns out it's still possible for the average even of 3 of the new process to come out worse than the average of 3 of the old process, but it's much more skewed in your favor now. And in fact, looking at these numbers, 97% of the time you will in fact show that the new process is better than the old process using this 3 against 3 comparison when you're finished. Those of you that are into math or something, you may have heard of this central limit theorem, which says that if you average enough things together, it always approximates, it comes to be a normal distribution function. And this is a clear evidence of that. This blue, you can see, is definitely not like a normal distribution function, but after you've averaged 3 of these things together, it's starting to look like a normal distribution function. And if you averaged a few more in, it would start to look very much like a normal distribution function. So, some final words of caution. How am I doing for time? Ah, almost perfect, okay. So, even if you're done with all this and you have concluded that the result is statistically significant, you have to heed what I call the scope of the comparison. And I've been a little bit tongue-in-cheek here, but this to help you remember these things. If in fact all of your data was collected on a Monday, the conclusion of the experiment may only apply on Mondays. I mean, that's the sort of thing to remember. I mean, it happens sometimes. I mean, in labs where they always change out the chemical baths on Monday morning, if you always do your experiments on Monday morning, you may get a result that you can't replicate on a Wednesday. So beware of that. Likewise, if all the data is from a single tool, it may only apply to that tool. If it all used identical wafers, the conclusion may only apply to those wafers. And this is a real hazard in photovoltaics. Like, for example, wafers from a particular ingot in multicrystalline silicon, the process may not work on wafers even from a different ingot from the same manufacturer. And then if one person did all the processing, that conclusion may only apply if that person does the processing. It could be some quirk about how they do it. No matter how hard they try to explain how to do it to the next person comes in and may not get the same results. So, people often want to say, okay, well, I want statistical significance because I've been told it's good, so surely if I keep everything the same except the experimental factors, that's a good thing in terms of reducing noise in the experiment. And the answer is yes. If you do that, you're most likely to get a statistically significant result because you will have reduced the noise in your experiment. But keeping all these other things fixed gives you a very narrow scope for your conclusion. And what that means, again, is that it may not be repeatable even under slightly different circumstances. And so some of my recommendations actually, and these things all are sort of counterintuitive to what I'll call a purist in the scientific method, perhaps, but it definitely works better in the long run. So actually, if you can spread your replicates across multiple days, it's typically a good thing to do. Randomize the run order so that you avoid misinterpreting process drifts as being an effective effector. Now, what do I mean by that? Like if you are going to do something 10 times, don't do process A 5 times and then do process B 5 times. You're much better to do A, B, A, B, A, B, A, B, A, B, because then if there's a drift with time, it will affect both A and B equally rather than it appearing that B is better than A when really that was just a drift that had nothing to do with the change from A to B. If wafer quality is the main source of variability, consider using an assortment of wafers. Rather than what your mindset is, which is probably, I want to do all of my different tests on exactly the same wafers. In fact, I'll even break this wafer into little pieces to make sure that they're all exactly the same. There's a hazard in doing that. And then this is really hard, I admit, but if you can get replicates using different people or different tools or different process materials, then you really start to have confidence that what you've got is robust. But frankly, most people in the world don't have that luxury, not even those of us in an industrial setting. So the bottom line is that the most valuable results are in fact those that others can replicate. And this is almost a philosophical point. I mean, frankly, in PV, unless your result gets ultimately put into high volume manufacturing, really, what is the point? We're not in PV just to explore science. You can go get a science degree if you want to do that. We're actually trying to do something useful, I think. And then another thing, which is one of the reasons why I'm here, I suppose, is that really, in order for results to be robustly generic, an ultimate goal would be to actually get correlation going between different R&D labs. And if 2 different labs, like on opposite sides of the Pacific, can actually get the same result, then with different people and different tools, then probably it's a real thing. Finally, I get asked to review a lot of articles that get submitted to publications, and I'm a real stickler for this. Not all of my fellow reviewers are so harsh. But I can tell you, if it comes to me, please show the statistical significance of your results and clarify the scope whenever you do it, because if you don't, you'll probably get a memo back from me that says, please do so. With that, if you happen to be in the Bay Area, please come visit us at the Hanwha's Advanced R&D Lab. We're right there. So if you fly into the airport, which is right up here, you have to drive about 30 minutes to get down here. But it's a nice little spot. That's what it looks like. And I'm pleased to say that of the 18 people that currently work with me in my lab, we are of 9 different nationalities, so including 2.5 Australians. I'm half Australian, so that's anyway. With that, thank you very much, and I'll answer any questions.
Yeah. Thank you, Paul.